My name is Tairone Leão, and I'm a soil physicist at the University of Brasilia. Today we're going to talk about numerical investigation of flow stability and transition from Darcy to Darcy-Forchheimer regimes in a porous medium proxy. This is the structure of this presentation. And why are we working on with Darcy's law and flow in porous media? Our motivation is because we're working with environmental physics, especially modeling the flow of water in natural porous media, mainly soils and weathered rocks. So here you have an example of those systems, and here on C you have an example of interaction of surface water and groundwater in carbonatic rocks. So the main component of the models for modeling saturated flow in porous media is Darcy's law. Here you have the generalized form of Darcy's law in 3 dimensions. In all forms, you have an average velocity vector, a pressure gradient, and the coefficient for this relationship between velocity and gradient is the permeability. Kappa tilde here is a permeability tensor, and mu here is the dynamic viscosity of the fluid. It's usually easier to model the same system in 1 dimension, so we can reduce Darcy's law to 1 dimension, and this causes the permeability to be a scalar permeability. So it's much easier to model this as a scalar than to model it as a tensor. For generalized flow in porous media, the governing equation is the same equation that governs the flow of all fluids, which is the Navier-Stokes equation. The full Navier-Stokes equation here for an uncompressible fluid has the time derivative of the velocity field, the nonlinearity, pressure gradient, the Laplacian of the velocity field, and some body forces. For flow in porous media, we usually neglect the time derivative of velocity field and the nonlinearity, and we are left with the Stokes equation. The divergence of u being 0 here is the incompressibility condition that we assume because we're usually modeling water. When you state Darcy's law in the language of Navier-Stokes equation, you see a similar form of an average velocity vector here as a function here of the pressure gradient. Whole gz here is the body forces, but if the Navier-Stokes equation and Stokes equations resolve the flow in every point of the domain, with Darcy law we don't need to resolve the flow in every point of the domain. The permeability tensor here, or the permeability in case of the scalar in 1 dimension, acts as some sort of averaging of the flow properties to the porous media. So it simplifies the process of modeling flow in porous media. There should be some connection between those 2 equations, both in space, where you can link Navier-Stokes and Stokes systems in free fluids to Darcy's law for fluids flow in porous media, and there should be some form of derivation of Darcy's law from the most general equations, which are the Navier-Stokes equation and the Stokes equation. The theoretical justification is based on the homogenization theory, which is usually a form of expansion, a symptotic expansion of the velocity field here and the pressure field, and this homogenization will result in a theoretical justification for Darcy's law. When we talk about stability of flow in porous media, when we talk about slow flow, which would in theory be governed by Stokes form of the Navier-Stokes equation, we ignore the time derivative of velocity field, and we also ignore inertial components. It's usually easier to generalize inertial components as non-Darcy effects or non-linear effects, because inertial effects are complex and there is a lot of other things involved in inertial effects. So we're going to call the inertial effects non-Darcy effects. So in Darcy's law, we ignore these non-linear effects, the non-Darcy effects, and are left with the linear law. So the average velocity field is a function of a gradient of the average pressure field, and the proportionality constant here is the permeability of the system. Either scalar permeability, or if you have an isotropic and heterogeneous system, or a scalar permeability if you have an isotropic and homogeneous system. When the non-Darcy effects begin to be important, you start to have nonlinear effects here, and Forchheimer made a correction to Darcy's law, including a nonlinear term here, which is a quadratic correction in terms of the velocity fields. He also proposed cubic and higher order corrections, but this is the simpler one when you're talking about the beginning of the influence of nonlinear effects, which are measured, you can say they are measured in some form by the beta coefficient, which is related to nonlinear effect. So both equations can be used to describe the porous medium, and they can be linked to Navier-Stokes equation in the case of maybe Forchheimer correction and Darcy's law to create a Darcy-Stokes here system, or Darcy-Forchheimer-Stokes system, in which free fluid enters into a porous domain. This can be done, the measuring or determining those coefficients can be done experimentally, but today we are worried about numerical simulation of those systems. So we can create a simulated porous medium, and we can define flow properties by direct numerical simulations or direct numerical solution of the Navier-Stokes equation. And when instability develops, or even in the case of fully developed turbulence, we have simplifications for the direct numerical solutions, the form of large edge simulations and Reynolds average Navier-Stokes equations, which are developed used to deal with turbulence in these systems. So in essence, we can use those systems to calculate flow parameters, and then we can use those flow parameters to calculate permeability and either permeability and the beta coefficient here, if we're talking about Darcy-Stokes only, the permeability, and if we're talking about Darcy-Forchheimer systems, the permeability, and also the non-Darcy or beta coefficient in this case. For beta is usually also called Forchheimer coefficient. And how do we measure the contribution of inertia or nonlinear effects? Usually in porous media, we have an adaptation of the Reynolds number for flow in porous media, which we include here some characteristic dimension of a porous media. If you have homogeneous and isotropic porous media, it could be the pore diameter, which is difficult to model in some cases, or the particle diameter, which is a representation of the pore diameter for a homogeneous and isotropic system. For the Reynolds number for porous media, usually stability or small contribution of inertia of non-Darcy effects is for Reynolds number less than 1. Other forms or corrections of the Reynolds numbers have been proposed for porous media. One is the hydraulic diameter or porosity correction, which we're going to include a correction here for phi, which is the porosity of the system. A correction based on the permeability. So here we need the permeability calculated using some form of Darcy's law to calculate the Reynolds number. This can usually be contrasted with the Reynolds number for free conduits or for conduits without porous media, which is calculated by using some form of hydraulic diameter, which depends on the conduit's geometry. So all of this can be useful to some extent to porous media, but this one for free flows usually is not very useful for porous media, but can be used as a means of comparison with the other ones. More recently, there has been it was proposed the Forchheimer number or the based on the Forchheimer equation, which takes into account the beta and kappa coefficients calculated from the Forchheimer equation. So you need to data for the Forchheimer equation to be able to calculate the Forchheimer number. We're using kappa 0 here because not to confuse with kappa calculated from the Darcy's law. This implies that for Darcy's law can be written in this form, or the Forchheimer equation can be written by substituting mu over kappa by mu over kappa 0 plus beta whole u. And if the velocity becomes too small, then as the velocity goes to 0, Darcy-Forchheimer equation reduces to the traditional Darcy's law. Zhang and Grigg in 2006 proposed the non-Darcy effect as a percent error induced by ignoring non-Darcy effects. So this is a very convenient number because it will give you a percent error if you start ignoring the nonlinear terms. Our simulation was done with the open form version 9, and this is the domain for our simulation. We have a porous domain, omega 2 here in the center, and we have two non-porous domains. The flow is from left to right, and the idea is to understand the boundary between the non-porous domain and the porous domain, and to see what happens when the flow exits the porous domain, if this can influence the stability of the system. This is the grid used for our simulations, and this is the parameters used in our simulation. The usual approximate density and viscosity of water at ambient temperature. We have the length of the porous media and the radius of the obstacles here in the millimetric to centimeter range. We have a quasi three-dimensional geometry here of the domains, but we set z at a very small value, the z dimension at a very small value, to simulate two-dimensional porous media, because OpenFOAM does not deal with two-dimensional geometries. This is the grid dimensions here. Delta y, delta x were fixed at 0.01 times 10 to the minus 3. Delta t was 0.001, and the maximum time was 5. The inlet kinetic pressure started at 10 to the minus 5, and then one was increased tenfold until instability was developed. Outlet kinetic pressure was fixed at 0. We used the OpenFOAM with the PCG solver. We used IcoFoam with the PCG solver, which is the incompressible solver for OpenFOAM, with the piezo algorithm. So this is the results for our system. You can see here the magnitude of the various forms of the Reynolds number. The Reynolds number for porous systems, the Reynolds number for non-porous systems, the Reynolds number considering the porosity correction, the Reynolds number considering the permeability, and this is the calculated permeability at each pressure gradient. So we calculate the direction by setting the pressure gradient, the flow velocity, and using a straight application of Darcy's law, we calculated the permeability of each step. You can see here that under direct numerical simulations, when the flow is stable, the permeability varies little. It's not constant. It's never constant, but the variation is too small. And the critical value of the various forms of Reynolds number here is around 1 to 10 for most systems. If you look at the numerical simulation here, you can see that there's some symmetry of the flow system, and there's not the development of jets of any forms of stabilities. So this is a pattern that we observe in all forms of the flow when the velocity or the pressure gradient is small and the velocity is small and the flow begins stable. So this symmetry justifies here the use of Darcy's law and indicates the symmetry of the velocity field. So this is the velocity fields, indicates that there is no disturbance. The flow velocity here is increased within the in between the obstacles, but quickly returns to the flow velocity as it was before the obstacles in the porous medium. As the velocity increase, the flow velocity increase, you can see the start of the developments of jets here. So you have jets here in the outlet, which is the concentration of areas of higher velocity on the velocity fields. So this here indicates that we left the Darcy regime here and we enter the Darcy-Forchheimer regime. You can see the same pattern as the velocity increases here, so the flow becomes stable after all. The velocity here of the movie, it's much greater than the velocity for time constraints. It's much greater than the velocity that we actually see in the output of the simulation. So we see concentration of higher velocity here, and we have concentration of jets that reach the end of the domain. So the presence of the buffer zone here is not enough to mitigate the disturbance of the velocity field as the velocity fields increase. So increasing even more, now you start to see the development of instabilities on the velocity fields. So you have a periodic movement here on the velocity field and some detachment of vortices here, indicating maybe the development of von Karman vortex streets here. But it's still possible to measure the Forchheimer coefficients or calculate Darcy law using this system. You can see here that Darcy's law is affected. The calculation of permeability using Darcy law, we have smaller and smaller values as the development of instabilities increases. So here we have instabilities. At this point, the simulations were no longer stable. The current number started to become too high, and we're using simple computing system. Each simulation we're taking around 1 hour to 1 hour and a half. Was no longer stable under direct numerical simulation, so we started to use Reynolds average. We tested Reynolds average Navier-Stokes equation using the K epsilon model, the two equation model, to see if we could continue with the simulation. What we see here is that using the Reynolds average Navier-Stokes equations, it simply averages out the instabilities. So the flow starts to look like it was before, although it really is not as it was before. We also tested large edge simulations. We also tested large edge simulation. So large edge simulation, there's a subgrid scale which is not model and a larger scale which is model. This is the K equation model here of Kim and Manon, 1995. And when we use the large edge simulation, what you can see is that the large edge simulation capture the instability, which is more in line with what was seen before when we were using direct numerical simulation. You can see that as the velocity increases, the various forms of the Reynolds number increase. You can see the development in some instance even of turbulent behavior and full developed instability here. Even though there is some periodic structure, here's the flow is much less, the velocity field is much less stable than in previous case. And all of this affects the calculation of the permeability. So all of the forms of the Reynolds number here were able to detect the transition. The problem is, what is the critical Reynolds number in all cases? Here we have the calculations using Darcy and Darcy-Forchheimer equations, you can see that as we increase the velocity, the average velocity of the flow here, only the first 3 points, which we show that were approximately constant, were able to fit the traditional Darcy's law. So this dotted line, dotted line here is the predictions using Darcy's law. So we have kappa at the order of 1.25 times 10 to the minus 7 meters squared meters. And here you have in red the simulation, the calculations from Darcy-Forchheimer equation. You can see here that the order of magnitude of the permeability here is lower, and there's a constant deviation which grows larger from Darcy's law as the flow velocity increases. You can see here that the point calculated, the point calculated using Reynolds average Navier-Stokes equations deviates from the predicted line, indicating here that the points calculated using large edge simulations were more consistent with the overall trend, and that's what we saw when we looked at the data. This is the Forchheimer number and the non-Darcy effect. So the error ignore the non-Darcy nonlinear effects here. You can see that the Forchheimer number here, the transition, it's around 0.1 to 1, the value of the transition for when the nonlinear or non-Darcy effect starts to become significant. And it has been proposed in one of the literature that we mentioned in this paper, a critical value of 10%, which translates to around 0.11 to the Forchheimer number. So this is consistent. So the Forchheimer number is also another alternative to estimate when the nonlinear effects become significant, and the critical value around 10% seems to be reasonable within this simulation in this study. So the conclusions of this study were that the permeability is a function of flow velocity. The assumption that permeability is constant in Darcy regime is not consistent with numerical simulation, and several experiments in the literature also agree with this statement. All dimensionless numbers investigated can be useful in detecting deviations from the linear regime. The question is what the critical values are in each case. As nonlinearity increases, the effect of jets and instability on fluid flow and mixing becomes more evident. The effect of nonlinearity and turbulence in subsurface flows and contaminant and heat transport needs to be better investigated using models and observations. This is especially for what's called real porous media, which are very complex and much more complex than simulated porous media. These are some of the references I used for this study. Please feel free to contact me if you have any further questions. Thank you.